So good morning, good afternoon, and good evening. First of all, thanks for joining this presentation. As Srinivas said, my name is Magnus Andreasson, and I work with product management at MSC. And it's a pleasure to talk about the brand new MSC Nastran 2017 release, which was posted on the software download center just last week. And also Patran 2017, which is currently in the middle of its beta program. So if you want to use the beta version of Patran 2017, please sign up to participate in the Patran beta program. So this release of MSC Nastran, it delivers new capabilities and improvements to already existing functionality in many of the key themes we have for several MSC products. And those are dynamics and acoustics, which is one of the key areas for Nastran. Advanced nonlinear, which means solution 400. Roto Dynamics, optimization in solution 200. Numerical methods and high performance computing is an area where we always put a lot of effort to improve. And also on the user interface side, I will talk about Patran 2017, but also a little bit on the fairly new HDF5 results database, which we have in MSC Nastran. So let's start with dynamics and acoustics, which is one of the core areas of MSC Nastran. So starting on with the embedded vibration fatigue. So MSC Nastran, the embedded fatigue, which is also called NEF, it was first introduced in version 2013, and then it included stress and strain life methods, factor of safety, parallel processing, among many other things. Since then, we have added significant capabilities to the NEF, like spot welds and seam welds. We have multi-axial assessments. We have 2- and 3-pass fatigue analysis in order to make the turnaround time as short as possible for complex models and loading. We recently added surface result stresses automatically for solid element models, and we have also super element support, for example. Now in MSC Nastran 2017, we will extend the NEF capabilities to also offer the possibility to perform fatigue analysis in the frequency domain. That includes new technology to random response and deterministic simulations for fatigue life and damage assessments in the frequency domain. And you can do that both in direct and modal frequency response, meaning both solution 108 and 111 is supported, together with also solution 200, the optimization solution sequence. So what is vibration fatigue? Time domain fatigue, those analysis consists of normally defining a load with respect to time for all the inputs you have on your model. You run a standard, a static or transient analysis in which you recover the local stress time histories, and then you feed those stress histories into the fatigue solver and to calculate fatigue life and damage. And that's the most accepted methodology and a basic time domain fatigue analysis. On the other hand, in the frequency domain fatigue analysis, it consists of defining input power spectral density functions, also called PSDs, which can be determined from the input time history loading, uses the FFT method, so the fast Fourier transform. So you convert time histories into the frequency domain in form of power spectral densities. Or you can also define those PSDs manually. And the inputs, they can be random in its nature, or it can be deterministic in form of sine or narrow band sweeps, or combinations of those. So a frequency response is run instead of a static or transient analysis, and the response stress PSD is determined, and that's what we use for the fatigue calculation instead of the stress time histories. So instead of time, we work in the frequency domain. And why would you want to do that? So frequency domain methods are perhaps more widely used than time domain, at least in many industries. So for example, for aircraft structures, for satellites, wind energy, and particularly powertrain exhaust systems where you have by nature a harmonic loading onto your structure, since you have a rotating system. It tends to be harmonic. It can also be components attached to vibrating structures, rotating structures, and offshore, for example. So in frequency domain, you often see benefits over time domain method, and that's the intuitive way to find the dominating frequencies and study the eigenmodes that act at those frequencies in order to find the root cause of your structural dynamics problem. So that is also valid for when you go to the fatigue side. So if you do fatigue in the frequency domain, you have a more intuitive way to find your root cause. So MSC Nastran is the premier choice and the leader for dynamics analysis. So this is a natural extension to the vibration capabilities to quickly turn the output responses from a direct or a modal frequency response into fatigue life and damage predictions. The fatigue life calculations is now a part of the frequency response and random vibration analysis. So there's no need to do the fatigue calculation as an extra post-processing activity. It's now embedded in the solution sequence and the flow of data. That means very large models can be analyzed, like full car bodies and truck models, for example. Since most calculations are done in core, we try to reduce or eliminate the amount of files that needs to be written to the scratch area, and that reduces the disk space requirements. We've seen reductions up to 90% over traditional methods, and that means you also have a possibility to speed up the overall analysis time, since writing to a disk is a time-consuming activity. And finally, you also have the possibility to do optimization with the objective or the design constraints of damage and fatigue life. So that's also possible in solution 200 solution sequence. So a few words about the capabilities for the embedded vibration fatigue. We have both stress life and strain life in this first release of the embedded vibration fatigue. We have random loading, which can be single input with or without static stress offset. And it can also be multiple input loading, where you can also add the cross correlation between the different inputs. You can have deterministic loading, which may be a single or multiple sine waves. It can be narrow band, or it can be sweeps of those. And all of those types of loadings, they can be assembled into load events and sequences to make up a realistic duty cycle. And in addition to this, we have the capability to automatically convert time domain loading into equivalent PSDs, so going from time domain loading into frequency domain. That is done in the vibration fatigue using the FFT utility, which is provided within our capability. So that enables an easy conversion from time to frequency domain so that time domain signals can be used directly in frequency domain. So if you have your traditional fatigue calculations set up in time domain, we have an easy way to convert into frequency domain using the time to PSD conversion. So here's one example of a component fatigue analysis in the frequency domain. So modal frequency response analysis of a steering knuckle where you have multiple events and load cases. The time signals are converted to power spectral density using the time to PSD utility. And you can see here that the results, those are reported for each event, and finally also a total damage for the duty cycle, so a sum of the damage. And in this case we look at the element centroid for the results. That means that the grid ID is 0, but you can also calculate the fatigue life at the grid locations. Here's another example that also demonstrates the conversion from time to frequency domain, and it's a truck cab, which is normally it's run in solution 112, so modal transient response, where you have 12 input signals consisting of 4 mounting points of the cab to the frame, and then you have 3 directions in each one of those mounting points. The whole duty cycle, it consists of 10 different events, and the time histories are transformed to PSD using the time to PSD utility. We solve eigenmodes up to 80 Hz, which in this case is around 60 modes, and then we add residual vectors to the loading points to increase the accuracy of the modal solution. That is also the case for the modal transient analysis. And then we want to compare the accuracy of the results, some of the computational speeds, and the ease of use of the 2 different methods. And of course the accuracy is of high interest, and it can be shown on this real-life structure of a truck cab that the calculated fatigue life is within a factor of 2 if you compare between the 2 methods, meaning time and frequency domain fatigue calculation. And for fatigue assessments, that's in most cases acceptable and is often considered to be a fairly equivalent result, as it normally corresponds to about 5 to 10% in stresses only. The frequency domain fatigue simulation may be significantly faster compared to the time domain due to much less complex loading histories once they are converted from time to frequency domain. Because then you go to the PSD matrices, which reduce the resources and the amount of scratch file data required. And also, when it comes to some pros and cons, you have the more intuitive root cause analysis, and we can output a CSV file containing the input PSDs, stress transfer functions, and also the resulting PSDs, so that you can easily find the most critical frequency for the fatigue life and see which modes contribute the most at those frequencies. So it's a more intuitive way to directly do root cause analysis for the fatigue issues you may encounter. A few remarks about the embedded vibration fatigue in MSC Nastran 2017. There's full pre and post processing that's supported in Patran 2017. So if you want to try it out, please sign up and download the beta version of Patran 2017, which is available as we speak. I also want to push a little bit for a brand new user's guide that covers everything about embedded vibration fatigue, which is delivered with with this version of MSC Nastran. So it can also be downloaded from the software download site, same location as the Nastran installer. And also there's a new license required for MSC Nastran embedded vibration fatigue. That was it about fatigue, so let's move on to more dynamics and acoustics. For those of you who are working with dynamics and particularly Vibra acoustic simulations in MSC Nastran, the new peak out capability will potentially reduce the effort you have to put in to do different type of participation analysis. Using what we call the peak out, the user specifies a number of response peaks that should be detected in the frequency response results, and at those peaks the requested participation factors are automatically extracted. So there's support for PF panel, PF grid and PF mode, so panel, grid and mode participation. And some of the benefits is that it eliminates the manual identification that needed to be done by the analyst to find the peaks. And it can potentially reduce the number of Nastran runs required to perform panel participation calculation, because you can basically now do it in the first run. Previously you had to do a first run, inspect the frequency response functions, and then find out at which frequency you want to have the participation factors, and then do a second run. And there's a new case control command to control the peak identification called peak out, where you can specify how many peaks you want. You can specify the separation, the minimum separation between the peaks, lower and higher frequency of interest. And you can also determine if you want to look at displacement velocities or acceleration results, or if you look at fluid grid output, you can decide if you want to have them in linear scale, in dB, or in dBA scale. In combination with the peak out case control command, we also added a new option on the solution keyword on the panel, grid and mode participation case control commands. So solution can now equal peak, which activates the automatic peak frequency extraction. So here's just one example where you say peak out, you want 4 peaks with a minimum separation of 2 Hertz. And then for PF panel, you say solution equals peak. And then Nastran will find 4 peaks, the 4 highest peaks, and calculate the panel participation at those frequencies. So here's a use case of an automotive car body and its cavity. So you specify the peak out, which says I want 3 peaks, I want a minimum separation of 5 Hertz, and the acoustic response should be in dB scale. And then you set up 2 subcases, and in each subcase you have PF panel and PF grid for panel and grid participation calculation, and solution set to peak. And then you run the solution to run this job in MSC Nastran. And you can take a look at the results from this test case. So in the FO6 file you will get a confirmation of the peaks that were found by the automatic peak extraction. And in this case it's 26, it's 120 and 199 Hertz. And as you can see, of course, it corresponds to the highest peaks in the frequency response function from this analysis. And then you can post-process your grid participations as a contour plot or the panel participation more as a polar plot in order to see the direction and the magnitude of the different panel contribution. Moving on to next topic, which is mid-frequency acoustics. So when performing modal, dynamic and acoustic simulations in the mid-frequency interval, it can be from 200-300 Hz up to 1 or 2 kHz. The modal density starts to get really high and the modes are very less separated. And that means that even a small perturbation in the model in terms of geometry, perhaps material or thickness, it can result in significant changes to the response. So that is why a probabilistic approach will provide some more statistics to the results in terms of confidence interval and mean value, for example, in addition to just one deterministic result. Now, the mid-frequency capability allows the user to efficiently run a probabilistic Monte Carlo simulation in solution 111. And during that you handle your model uncertainties using the non-parametric variability method. And this method, it adds a variability directly onto the modal matrices, so it's a very efficient method since you don't need to resolve your eigenmodes. It also makes it very easy to run a number of analyses within just one solution 111 simulation job. And then you can post-process the results in a more statistical manner. Since this relies on running a number of frequency responses, it can be hundreds of frequency responses within the same MSC Nastran job. We use the distributed memory parallel capabilities of the already existing frequency response in Nastran to reduce the runtime for large models and many frequency response runs. And it shows very good scalability with respect to DMP. So it's an easy interface. You can easily convert your deterministic solution 111 to probabilistic type of analysis with a Monte-Carlo case control, where you say how many samples you want and optionally a random seed to feed the random generator. And then you have a Monte-Carlo bulk data entry where you specify the variability parameters on both the structural and the fluid, on the mass, stiffness and damping matrices. And then after you've run your job, you can post-process in something that is called a PLT viewer, which is actually a post-processing tool from Patran, which is now provided within the installation of MSC Nastran. And a description of how to use the PLT viewer if you're not used to that tool, that's found in chapter 12 of the Dynamic User's Guide. So have a look at chapter 12 in Dynamics User's Guide for an overview of this method overall and also how to use the PLT viewer. So here's a small example. A small demo model of a car body and cavity, which also includes a poroelastic material for damping. So we make a probabilistic simulation using the Monte Carlo capabilities. We run 20 samples, meaning basically 20 jobs, and we have a variability on the structural stiffness of 0.005. So this is how it looks in the input. So it's very limited amount of input you need to add to your already existing model. And then you can post-process this, the probabilistic results, like the mean value and confidence interval, 90% confidence, both for structural and in this case also for the fluid. So it shows that already from fairly low frequencies there's a significant inference from the variability on this particular model. Here's one more real-life model. It's a fully trimmed Vibra acoustic car body model. About 20 million degrees of freedom. There's 6 subcases, in total 1,000 forcing frequencies. And on those, on this model, we run 128 random samples for each subcase. So there's a lot of frequency response calculations going on. And we did run this model for a number of different DMP processes. And going from a serial run to a DMP16 run provided a 10x speed up, which is really significant in this case. So DMP can really reduce the runtime significantly for these types of problems. Moving on to the advanced nonlinear in solution 400, we've added a couple of things. For example, the Anand model for solder creep. So for manufacturing of integrated circuits, you use solder to connect the modules onto the printed circuit boards. And the temperature-dependent properties and creep characteristics of the solder, it has significant influence on the performance and the durability of the IC. So the Anand creep model, it's widely used and accepted in this industry to simulate the performance and the behavior of solder material. So we've added the Anand creep model as a new option on the existing Mat VP, so the viscoplastic material in solution 400. So there's no new material entry, it's just an additional option on the already existing Mat VP. So it's just one example where you can see you have a solder joint between the pins and the PCB on an integrated circuit. So here's one example, an axis symmetric analysis of solder balls that is used in a flip chip integrated circuit package. And the purpose here is to study the development of creep strains under thermal loading conditions. And the material of the solder itself is temperature dependent, and we use, of course, the new Anand creep viscoplastic model to study the development of creep strains. So to the right, on the pictures on the right, under the temperature loading, going from 20 degrees up to a working temperature of 125 degrees Celsius, we see some primary creep strains developing in a part of the connection between the solder and the chip. Next in solution 400 is support for cohesive contacts for the glued contact capabilities. So in many products like airplanes, cars and so on, we want to assemble more and more different parts together, and the assembly process, it can be done through different connector methods like rivets, bolts, different type of welds or adhesives. Sometimes you want to model each and every one of those connectors, but sometimes it's too complicated and time consuming to model them all in detail. So then glued contact is a convenient way to simplify the connection process. However, if you use the standard glued contact, that will most probably result in an overly stiff connection because of the high stiffness of the glued contact compared to the discrete connectors which are there in reality. So the cohesive contact, it offers a way for the user to control the glued stiffness in both the normal and tangential direction, and in that way you can overcome the high stiffness or the too high stiffness coming from the standard glue. And this works basically for all types of glued contacts. It can be in linear analysis, so solution 101 to solution 112 and solution 200. And it can also, of course, be used in solution 400. And it supports both the general and the permanent glued contacts. Of course, in the dynamic solution sequences, they can only be permanent glue. And it's only supported in segment-to-segment contact. If you're familiar with the contact technologies of MSC software, the segment-to-segment contact is the most recently developed method. And for the cohesive glue, that's the one you should use. So the user interface for cohesive contact, you define the stiffness values of the cohesive contact on the geometric contact parameters bcom PRG, where you define both the normal and tangential stiffness of the cohesive contact. And those can be constant values, but they can also be dependent upon relative displacement or on temperature using tables. So here's one example. It's a single shear example with 3 plates, and the top plates have 6 contact bodies, each region representing a discrete fastener. And we have 2 different setup of cohesive stiffnesses used. In this case, it's constant values. So we have 2 different bcon PRG, where you give the normal and tangential stiffness. Running this simulation and compared to the regular glue, the model is fixed on one side and then it's just pulled on the other side. And as expected, you will get higher, larger displacements in the actual direction in the model with the cohesive glue stiffness set, because it's significantly lower than the default stiffness from glued contact. One can also print the forces and moment resultant for each of those regions. You can print those to FO6. So you have to specify a reference grid around which the forces and moments will be summed. But then you can print those so you can get kind of an estimate of the forces going through each connector or each connection region. Moving on to Rotor Dynamics. We've done some enhancements in Rotor Dynamics. In this case, it's a transient analysis with unbalanced load. Now it's possible to include the mass and speed correction terms to account for inertia and gyroscopic effects when you add the unbalanced mass. And those terms can have a significant effect depending on the rotor and the amount of unbalanced mass. So you can have, in this release, you can apply either mass correction, speed correction, or the both of those corrections simultaneously. And in addition to this, you can also post-process the generated correction loads through E-points you specify on the unbalanced entry. There's also extended capabilities for structural damping of rotors, and this will allow you to have additional options to control the structural damping for individual rotors, especially when you have several rotors. This is a more flexible way to add structural damping directly on the R-spin R entry. Previously you had to use only one parameter, which was then applied to all the rotors in the model. So this is makes it possible to do more accurate modeling of the structural damping of each individual rotor. And we also added capabilities to do modal analysis, including rotors. So the modal approach, as you know, has the big advantage that it can really produce a quick simulation using modal reduction with the eigenmodes compared to a direct response analysis. So this is really helpful for 2D and 3D models of rotors, which can be fairly large. So with this release, the MSC Nastran 2017, it's possible to perform modal complex eigenvalues and modal frequency response for rotors with axisymmetric and 3D elements. Also, we added the option to generate Campbell diagrams in solution 110, which wasn't possible before. And what you can see, going from a direct to a modal solution, it's an easy conversion. You need to change solution sequence number and add modal extraction. But for this model, it turned out to be a 91% reduction in solution time going from direct to modal solution. So in many cases for large models, it will save a lot of time. Moving on to optimization, where we've added enhanced capabilities in topology optimization. So previously it was very inefficient to add a lot of stress constraints to topology optimization, and there was no way to deal with stresses in low density elements, which could be highly inaccurate. So with Nastran, MSC Nastran 2017, we have an efficient adjoint method to calculate the stress constraints, and it includes also filtering of the stresses in elements with very low densities, since those are not relevant. And this has been requested by many users since we got the topology optimization introduced in MSC Nastran. So now it's possible to set up a topology optimization with a target to minimize mass under stress constraints in an efficient way, in addition to the more classic setup with compliance minimization under mass constraints. So now it's in many cases a more realistic and a straightforward way to set up an optimization problem. Second addition to topology is a maximum member size constraint. So that's in addition to what we already have as a minimum member size constraint. We can now also add the maximum member size. So this is useful in some manufacturing methods where you now have the potential to generate a design from the topology optimization that can actually also be manufactured using, for example, casting, where you may have an upper limit on the thickness or the member size of some walls in your structure, for example. So here's one example. You have an original mesh and you want to do topology optimization to reduce the mass. And the top figure, it shows with only a minimum member size and no maximum member size, and you see that you can get fairly thick members. And when you add the maximum member size, you see that you get more but thinner members for this topology optimization problem. And as I already mentioned in the MSC Nastran embedded vibration fatigue, the results from those analyses can also be used in solution 200 in the analysis M-freak and D-freak. So the type of responses you can use is the life, of course, the log of life, damage, log of damage, and factor of safety. So those can be used either as an objective function or as a constraint in an optimization task. Moving on to numerical methods and high performance computing. And in this release, we've continued the work on the Cms method, which is the optimized component modal synthesis, which is an enhanced analysis technology to quickly find the eigenvalues and eigenmodes for very large Vibra acoustics or acoustics models. It's very popular in the automotive industry to use those types of methods. So the new version of ACMS we released a new version in MSC Nastran 2016, which is now called the Accelerated ACMS method. It now supports generation of external superelements. And that can be, for example, an Adams MNF creation, or you have a powertrain which you want to reduce down to its A sets, which may be, for example, the main bearings and the cylinder liners, for example. So if you do those types of analysis, you can now use the accelerated ACMS. We also reduced the memory requirements for this ACMS version, and also we added DMP capabilities for fluid modes eigenvalue extraction. So a typical use case for the external superelement generation is, as I said, an engine block reduction to its mount points and cylinder liner and main bearings. And it can also be an MNF generation for subsequent Adams analysis. And for large models, ACMS can add significant amount of efficiency over the standard Lanchos method. So the accelerated ACMS method is now supported, which in most cases provides better performance and parallel scalability compared to the original method. So for this example, you see with an increasing amount of threads added to the solution, you get a quicker and quicker wall clock time, and the red bar is for the accelerated ACMS method, and the gray one is for the original ACMS method. So you see that you can get from somewhere between 50 and 100% difference in wall clock time. The first version of the accelerated ACMS, it required significantly more memory than the original ACMS. Especially, the memory requirement increased with the number of processes you wanted to use. So that had resulted in two different things. First, you couldn't solve really big models because you were limited by the amount of memory, and the number of SMP threads you could use were also limited by the amount of memory. So that means that you couldn't really get the performance gain from the new method due to memory requirements. So this has been addressed, and we now can see a significant reduction in 2017, especially for solid element models, but in general for most models you see 20 to 30% memory reduction with the accelerated ACMS method. So the DMP parallel fluid eigen solution. So for many automotive models, we see an increasing size of the interior fluid domain, and it also you want to go to higher frequencies. And that can mean that the solution of the fluid modes can consume significant time. So in version 2017 of MSC Nastran, when you run your solution 111 job with an interior fluid model and run with DMP, the solution of the eigenmodes for the fluid will be parallelized with DMP. And that is done in the frequency segment parallel Lanczos method. So we chop up the frequency interval into several pieces and solve each interval in a separate process. Here's one example. So the size of this fluid model is around 200,000 degrees of freedom, but there's a very large frequency interval resulting in several thousands of eigenmodes. In this case, over 3,000 modes. So when going from a serial to a DMP4 solution, we actually reduce the time spent in solving the eigenmodes for the fluid with a factor of 4. So it scales very well on those types of modal extraction of fluids. So that's a significant performance increase for large fluid structure interaction acoustic analysis. I will touch this very briefly because I see that time is running. We have a new robust method for something we call the auto MSET, and that's a capability in Nastran to automatically define relationship between dependent and independent degrees of freedom when you use rigid elements and MPCs. And sometimes the default method can have a problem when the constraints are not well defined. So this can be the case, for example, in Adams flex body MNF generations where you have interface points on RBE3 elements. That's one typical application area. So this new method can significantly improve the robustness of those types for those types of models. And in some cases, it also improves the performance. Here's just one example where the default method found a number of zero frequency eigenvalues which were not found in when you solved the same type of model in Adams, but with the new LU-sol capability, that issue was removed. So if you are using MSC Nastran to generate MNF files for Adams, and you see an issue with not finding all the eigenvalues, then you can try this new method. So moving on to the user interface. So in MSC Nastran 2016, we introduced a new database format which is called HDF5. So it's a data model for storing and managing data. So it's also optionally output by MSC Nastran with the MDL PRM parameter, and it can be generated together with OP2, or it can be generated instead of the OP2 file. So this type of database, it has a high precision, it has a built-in compression to reduce the file size. And it's also platform independent and have multiple scripting or programming languages you can use together with the data. For example, Python. So we support those in the major solution sequences. And the supported data types are all the major inputs and output data. And we continuously add more data to the output of this format. So if you want to try, add the MDL PRM HDF5, 1 to generate the compressed HDF5 file. Yeah, what's in this database? It's basically both inputs and outputs, all the model inputs and case control and parameters. And the output is definitely what we see in OP2 and even more. So we add more capabilities to output results in the HDF5 file. So the resulting file called H5, it can be open in the HDF view browser, which you can download freely from the hdfgroup.org. And there you can actually see the data and see the formats of each data block. So it's very easy if you want to do scripting. You know what the data looks like compared to OP2, where you have to do a lot of investigations. So here's one quick example using Python to access the data. So you need to run with Python, you need to download a couple of packages, NumPy and tables, but then you can easily open the HDF5 file and do your own post-processing on the results from Nastran. So it's very convenient if you like Python and have a need to do your own post-processing. So in MSC Nastran 2017, we add a number of new data types like complex eigenvalue summary table, composite element output, more fatigue, more acoustics results. We also add monitor points, which wasn't there before. And we also have a possibility to exclude the model data and also to exclude the rotational degrees of freedom results. If you have very large file sizes and you're not interested in the rotational degrees of freedom results, you can optionally exclude those. You can also, from Solution 400, generate intermediate HDF5 files so that you can post-process during during the time the simulation runs. So those are the major things we add in 2017, but we continue to add stuff also for next version. So this is, as we see it, the formats of the future for MSC Nastran results. And I will end with a few slides on Patran 2017, which will be released now slightly after MSC Nastran 2017. And some of the highlights, it's a common user interface look and feel now for both Windows and Linux, which used to be pretty different if you saw Patran on Windows and Linux. So it's a better, a more flexible user interface framework with docking, undocking features, spreadsheet widgets, improved plotting. So it adds a lot of value to the Patran product in its ease of use and look and feel. Patran 2017 also supports pre- and post-processing of MSC Nastran embedded vibration fatigue. And now for the first time we can also attach and post-process results on the HDF5 format in Patran. So here you see two pictures of Patran on Linux and on Windows, and you would have to look very carefully to find any differences. So it's a very common look and feel. So a few things about the features. You have tabbed viewports and output windows. So you see at the top of each viewport there's it's gathered by tabs, so you can easily switch from one viewport to the other. And at the bottom you see you can easily switch from console to command and selection window. The XY plotting has several enhancements, especially it's easy to zoom and pan using the mouse. You can zoom in at a specific area of the graph using your scroll bar, using your mouse wheel to scroll. You also have new shortcut keys. So using the Alt key on your keyboard, you will get in the user interface, you will see which keys you need to push to go directly into a menu. So for example, using Alt D, you get to the durability tab. or Alt L, you get to the loads and boundary conditions tab. So that's in order to reduce the mouse travel you need to do to get to the different menus. We also add a number of themes, so you can change the how the graphical interface looks like in terms of design and colors. So there's a number of different themes available in Patran 2017. You can also scroll with the mouse wheel through the tabs in the main menu, and you can also now scroll to zoom. So when you scroll in the graphics window, it will zoom, and the center is then set to the mouse marker. So it's very convenient to zoom in a specific area using the mouse wheel. There's also full support of the MSC Nastran embedded vibration fatigue, both in terms of pre-processing and post-processing. So for pre-processing, of course, you can define your fatigue materials, the loads and events. There's an efficient event handler. You can set up the fatigue parameters and, of course, also request different types of output. So there's a complete set of pre-processing capabilities. And for post-processing, you can do post-processing using different file formats. You can use the master DBO file or the new OP2. There's also an FEF type of file you can write from MSC Nastran, which can be post-processed in Patran, and also the HDF5 and CSV files. So there's also 2 additional CSV files containing, for example, the power spectral densities, both the input, the transfer function, and the output power spectral density. So here you see it's easy to identify the peak frequencies in the PSD in order to find the root cause of your fatigue life. Finally, Patran 2017 also supports the HDF5 results file written by MSC Nastran. So this is something I already mentioned. The benefits of the HDF5 support: it's high precision, it's compressed, and there's a new capability in Patran to attach the HDF5, where you can read both the model data and the results data sets. So here's a couple of examples. One crankshaft eigenfrequency analysis. So here's also a comparison between the file size, in this case for the HDF5, the compressed type of HDF5 file, it was 13.5 gigabytes, while the OP2 file was 17.3 gigabytes. So it's significantly smaller, but the biggest benefit of the HDF5 in Patran is that it attaches in seconds instead of minutes compared to the OP2. So for this 13.5 gigabyte file, it took 4.5 seconds to attach in Patran, and for the corresponding OP2 file, it took 4 minutes. And there's also other examples demonstrating the same type of performance benefits. So to conclude, the HDF5 is often smaller than the OP2 XDB or the master files, and it's very much faster to attach in Patran 2017. Some additional items. So the MSC Nastran 2017 is available now for download from our SDC site. The beta program for Patran 2017 will run until end of January, and we plan to release the official Patran 2017 just shortly after the end of the beta program. For the first time, MSC Nastran 2017 and Patran 2017 runs on Windows 10. And also on Linux, we have new platform support in terms of Red Hat, Enterprise Linux 7.1, which wasn't supported before, and also SUSE 11 Service Pack 3 is now supported. And also for the first time, we don't deliver any i4 versions, so it's now only one version for each platform, and those are pure long integers, so the i8 version is the one that remains maintained from now on. And for the vibration, embedded vibration fatigue, we have new license features. So with that, I thank you so much for your attention.